The purpose of this video is to discuss assignment number 7, which is infinite geometric series, and unit 9, which is in our unit on sequences and series. And so we haven't talked about an infinite series yet, but an infinite series is just a series that goes on forever. If we have an infinite arithmetic series, that's just a series that goes on forever, and we really can't find the sum of that series, even if it's just a simple one like 1, 2, 3, 4, 5, 6, 7. If that went on forever, we couldn't find the sum of that because it just continually gets bigger and bigger and bigger, and we simply can't find the sum of something like that because it never ends. That's not necessarily the case when we talk about geometric series. It depends on what type of geometric series that we're talking about. There's two types of geometric series: a converging geometric series and a diverging geometric series. The examples that we did, at least on our video, on our last assignment for assignment number 6, were all finite geometric series. And so then it really didn't matter whether it converged or diverged. But the difference is something like this. If we start off with, let's say, a number like 4, and the next number is 8, and the next number is 16, and the next number is 32, what's happening is that this is getting bigger and bigger and bigger. It's very similar to exponential growth. And if we were to graph something like this, just like we graph exponential growth questions, it looks something like this. This is diverging. This is getting further and further away from like the x-axis. And if this goes on forever, we simply cannot find the sum. Okay? We can't find the sum if it goes on forever, if it diverges and gets further and further away from the x-axis. However, if it converges, let's say we start with a number like 32, and then we cut it in half and get 16, and then 8, and then 4, and then 2, and then 1, and it keeps going, that is a different story. This is an example of something that converges. It's very similar to exponential decay type of questions, and it kind of approaches the x-axis even though it never really touches it. This will never get less than 0. It'll never touch 0, but it'll get really, really close to 0, like a half, and then a fourth, and then an eighth, and then a 16th. And it'll go on forever, and we can find the sum of converging geometric series. Let me give you an example of what one might look like. Let's say that I retire in a few years, since I'm as old as I am, and I go to the nursing home, and my favorite thing to do is to go downstairs, and I have a square that I like to color. And so I'm coloring this square, and the first day I go downstairs, and I have my square. It has an area of 24. Okay, maybe it's, I don't know, some square that has an area of 24 square inches. And I decided that I'm going to color half my square. And so I take some time and I do a good job of making sure that half my square is completely covered. How much did I color the first day? Well, if it has an area of 24 and I really colored half of it, I colored 12 square inches. So I'd go to bed, and the next day I'd wake up and get really excited because I'm going to color half of what's left. So I color in half of what's left of my square. And how much did I color the second day? Well, there was 12 left, and so I colored in 6. And then I go to bed, I wake up the next day, and I decide, well, I'm going to color the next half. And so I come downstairs, and I color in half of what's left. There was 6 left, and I colored in 3 of that. Then I color half of what's left. That's 1.5. And I keep doing that forever. Okay? Color in half of that, and then half of that, and then half of that, and half of that, and half of that, and half of that. Would I really get done with coloring the square? Well, if it went on forever, I would get really, really close, infinitesimally close, even though I would never really color in all the square. But if I got infinitesimally close, it's going to be that I colored really close to the entire square, which has an area of 24. So if I lived forever, I still wouldn't really get to 24, but I'd be so close that we would call it 24. And so this is an example of a converging geometric series that has a sum of 24. We couldn't do it if it was diverging, but because it's converging, we know that we can take the sum of that. Let's talk about how to do that without having an example where we're just looking at a square. And what I want to do is look at our formula that we came up with the last time that looked like this. S sub n equals a sub 1 times 1 minus r to the nth over 1 minus r. This is the formula for a geometric series, but it's a finite geometric series that we've been talking about. It always had a starting point and it had an ending point. We had a certain number of terms. N was a specific number. Well, let's say first of all that we're talking about converging geometric series. In a converging geometric series like this one, the r value, the ratio, is always going to be less than 1. And so, again, this is not going to work if the ratio is bigger than 1, because these numbers just keep getting bigger and bigger and we wouldn't be able to find a sum. But I want you to think about this. You're going to have to put some thought into this. If the numbers go on forever, but the ratio is less than 1, when I multiply two numbers that are less than 1, does it get bigger or smaller? Think about a half. A half times a half is a fourth. You can think about any number. A fourth times a fourth is a 16th. And it always gets smaller and smaller and smaller and smaller and smaller. So as n goes to infinity, this is 1 minus something that's getting smaller and smaller and smaller and closer to 0. So this, what's in parentheses here, is getting closer and closer and closer to just being 1 minus 0, which is really 1, or closer and closer to 1, which means that if it converges, our formula that we can use is just going to be a sub 1 times 1, which is a sub 1 over 1 minus r. This is actually a much easier formula to work with, but it only works, I mean, this is what we use for infinite geometric series. This is the infinity sign, or at least it should be. And it works in an example like with our square. If I were to take my square and I wanted to find the sum of the infinite number of terms, if this went on forever, I would take the first term, which is 12, and I would divide it by 1 minus my ratio, which is a half. Well, 1 minus a half is a half. If I take 12 divided by half, what do I get? 24. And so this is how I find the sum of infinite converging geometric series. Let's take a look at another example of one, and only one example this time, but it's going to be a problem that's going to have two parts to it. Let's say we have a bouncing ball, and let's say that we drop the ball from a height of 20 feet. Okay? And so it drops down 20 feet and it bounces, but when it bounces, it goes up 80% of its previous height. So it comes down, it bounces again, and it goes up 80% of its previous height. And it continues to do that until eventually it goes so fast and it's almost like it's touching the ground. But let's just say it goes on forever. So we know that the first drop is going to be 20 feet. We know that the second, when it comes back up, it's going to come back up 80% of 20 feet. So if we multiply 20 times 0.80 or 0.8, that means it's 16 feet, which means it's going to go down 16 feet. And then it's going to bounce back up 80% of 16 feet, which is 12.8. And it's going to go down 12.8. And that's going to continue forever until it gets so close to 0 that we really can't tell a difference anymore. Here's the question. What is my upward distance that it's going, and what is the downward distance that it's going? And then maybe we can figure out what is the total vertical distance that it's traveling, both going down and going up, if I were to add all those numbers together. Well, let's start by looking at the upward distance. This is a converging geometric series that looks something like this. It started going down 20. And the next time it went down 16. The next time it went down 12.8. And it continued to do that. And what we want to do is add all those numbers together. And it goes on forever. Well, we first have to know what is our common ratio. What did I multiply 20 by to get 16? It bounced up 80%, which means I'm multiplying by 0.80 each time. That is my common ratio. So I can simply find the downward distance. I guess I'm doing my downward distance first. I can find my downward distance by using our formula. The sum of the infinite number of terms is going to be the first term, which is 20, over 1 minus the ratio, which is 0.8. 20 over 1 minus 0.8 is 0.2. 20 divided by 0.2 is 100. That means, all in all, it traveled 100 feet going down. Well, what about going up? Well, going up, it started going 16 feet up. It's basically this same thing. It started going 16 feet up, and then it went 12.8 feet up, and then 80% of that. And so there's a couple ways I could do this. I'm going to choose to do it like this first. The sum of the infinite number of series or terms is going to be 16 over 1 minus the ratio. Well, that's 16 over 0.2, which is 80. And that makes sense because everything's going to match. We have a 16 and a 16, 12.8 and a 12.8. These two distances are going to match. It's just that we started out going down 20 more feet than what we went up. And so that makes sense that we went down going 20 more feet than what we went up. The total distance that it would travel, the total vertical distance, would be 180 feet if I add those two numbers together. So our assignment for tomorrow is simply going to be finding the sum of infinite geometric series. We're going to be able to write them in summation notation. We're going to be able to find the certain ratio of these type of problems, and hopefully this made sense, and we will see you tomorrow.